In this video, we're going to determine whether a function is odd, even, or neither. So the first thing I want you to note here as we talk about even and odd functions is that this is different than talking about the degree of a function. So obviously you can still have even and odd degrees of a function, but even and odd functions are actually talking about the symmetry of the graph and what this graph is or is not symmetrical around. So by definition, an even function is a function when f of negative x, so notice that we're essentially reflecting this x over the y-axis because it's a horizontal reflection that we're doing there. When f of negative x equals f of x for all of the x values in its domain. Essentially what this is saying is that the graph is symmetric around the y-axis. So here is our y-axis, and this is saying the graph is symmetric around it. The y-axis acts as a line of symmetry, and we can essentially fold over that line. Now, what this means, if you want to be a little bit easier, is if our graph, was at the point 2, 3, 1, 0, say it went down to a half 1 down here, and it came up to 0, 0 here, if this is what the right side of our graph looked like, essentially it would reflect over this y-axis here. So if we have 2, 3 as a point, then we have to, if we reflect it over the y-axis, the point negative 2, 3 would also be a point. So notice it's negative 2, 3, and it's reflected over the y-axis. The same thing would happen here. We would have the point 1, 0, so the point negative 1, 0 would also be on there. And then we'd have the point, half negative 1, so we'd have negative half negative 1. So we have this symmetry around the y-axis. So if we have an even function, we're going to test this equation right here. We're going to test and see if this function works, essentially if we apply a negative x to the inside of the function, if we apply a horizontal reflection, we're testing to see if that's equal to itself. And so you'll see that as we test it out, but what happens when we're testing for an even function is we're testing for, is this symmetrical around the y-axis? Now the odd function, on the other hand, is a function that is symmetric around the origin. So we test for this by seeing if f of negative x is equal to negative f of x. So essentially on this side we have a horizontal reflection, and on this side we have a vertical reflection. And we're checking to see essentially if for every point xy on the graph, the point negative x negative y is also on the graph. So if we apply this same function here, so say we had 2, 3, then we have 1, 0, and then say we have that 0.5, negative 1, and then 0, 0. So say this is what we currently have. Now, if we're going to test to see if this is an odd function, essentially all x and y points flip to negative x, negative y points. So we would go to negative 2, negative 3. Then we would go to negative 1, 0 would stay the same because 0 doesn't get flipped over that y-axis in any way. Then we'd have negative 0.5 and positive 1. So essentially this flips, and this graph essentially, if you were to rotate it 180 degrees, it would reline up on each other. That's what a reflection about the origin means. So if we rotate it 180 degrees, it will always line up on each other regardless of what we do. So here we're going to be testing to see if a function is even, if a function is odd, or if it is neither of these two things. So for each of these functions, we're going to test to see if it's even, odd, or neither. So remember, to test if a function is even, we need to prove that f of negative x is equal to f of x. And to prove if a function is odd, we need to prove that f of negative x equals negative f of x. So we're going to test it out in both, and we're going to see what happens. So for this first example with the even function, essentially what we're going to do is we're going to apply a horizontal reflection to this function because we can see we're multiplying by -1 on the inside. So if we apply that horizontal reflection, I have a -1 inside of the parentheses now with each of these x's. So I have -1x cubed, and then -7 times -1x. And I'm checking to see if that's equal to the original function of just x cubed minus 7x. So I take -1 to the power of 3, which is -1. Then I have x cubed. And then I take -7 times -1x, which is a positive 7x. And I'm checking to see if that's equal to x cubed minus 7x. And when I look at this, what I notice is that this isn't equal. I have a negative x cubed on one side and a positive on the other, and I have a positive 7x on one side and negative 7x on the other. Those are not the same. And as a result, because they are not identical, I can confidently say that this is not an even function. However, just because it's not even doesn't guarantee that it is odd, because even means symmetric around the y-axis, odd means symmetric around the origin, but there are situations where it's neither of those things. It's symmetric around something else, or it doesn't have symmetry at all. So what we're going to do now is we're going to test out the odd function, and we're going to see if instead this function is in fact odd. And in order to test if a function is odd, we have to test and see if the horizontal reflection is equivalent to the vertical reflection. So you can see here we're multiplying by -1 on the outside, and here we're multiplying by -1 on the inside. So we're going to test those two things, and we're going to see if they're equal. So here we can see that we have -1's being added to the inside, so we have -1x cubed minus 7 times -1x is equal to, we're checking to see if that's equal to -1 on the outside of the entire function. So if I start here by focusing on the left-hand side, I have -1 cubed, which is -1 and then x cubed. I then have -7 times -1x, which is a positive 7x. And then here, to simplify this right-hand side, I distribute the -1, so I get -1x cubed plus 7x. And what I notice when I look at these two sides of the equation is that they are identically the same. And because they are the same, I can confidently say that this is an odd function and that it is symmetrical around the origin. I have proof that this is in fact resulting in a true statement. We have a horizontal reflection that is equal to a vertical reflection. So because this equation right here is true, this function is odd and symmetric around the origin. So let's apply this to a second example here. So if we check if this is an even function, again, we're going to add the parentheses in here wherever there's an x and add a -1 into the front. So we're going to have -1x to the power of 4 plus -1x to the power of 2 minus 1. And we're checking to see if that's equal to the original function of x to the 4th plus x squared minus 1. Well, here I know that -1 to the power of 4, because it's an even power, is going to result in 1x to the 4th. I also know that -1 to the power of 2, because that's an even power, is going to result in a positive 1 and then x squared minus 1. And when I look here, what I notice is after I apply that horizontal reflection, what I notice is that these two sides of the equations are exactly the same. So I can see here that this is in fact an even function and is symmetrical around the y-axis. Now, if I hadn't done the even first, then I want to make sure I test out the odd function. Let's clarify that this definitely is even and that it is not odd. So we're going to apply this same thinking, but we're going to use the odd function instead. So we're going to do the horizontal reflection and the vertical reflection and see if they're identical. So here for the horizontal reflection, we add -1's in there. So we're adding those in. And then if we have a vertical reflection, there's a -1 on the outside of this entire thing. So again, I know that negative 1 to the power of 4 is a positive 1. I know negative 1 to the power of 2 is a positive 1. So that's what my horizontal reflection would look like. And here, if I distribute out a negative 1, I get negative x to the 4th minus x squared plus 1. And I can clearly see here that these are not the same. So I can confirm that this function is in fact not an odd function. So now you've seen an example where we have an even function where it's reflected around the y-axis. So let's test out one more example here. So again, we're going to test if f of negative x is equal to f of x. So here we add little parentheses wherever there's an x. So we take negative 1x to the power of 3 plus 2. And we're checking to see if that's equal to the original function of x cubed plus 2. Well, negative 1 to the power of 3 is negative 1 x to the third plus 2. And while the plus 2 part is the same on each side, unfortunately this negative x cubed on one side and a positive x cubed on the other result in these not being the same. And as a result, I can say confidently that this function is not even. So now let's flip over and test the odd function and see if this is in fact odd. So here we do our horizontal reflection first. So we do negative 1x to the power of 3 plus 2. And we're checking to see if that's equal to a vertical reflection, which means negative 1 on the outside, times x cubed plus 2. So here, negative 1 to the power of 3 becomes negative 1x cubed plus 2. And if I distribute out this negative 1, this becomes negative 1x cubed minus 2. And if I look closely, while the negative x cubes match, the 2 and the negative 2 are not the same. And as a result, this function is also not odd. So this is telling me that the function does not reflect around the y-axis because it's not even. It also doesn't reflect around the origin because it's not odd. So this is actually a function that is neither even or odd.